might be something new for most of you. So today we want to share what is the value of this technology in terms of a digital twin and how it might be, what is the landscape of the technology and how it might be implemented for business use cases, which we as a SoftServe operating with. So let me introduce our today's guest. Thus is R&D product manager, OLED R&D, and R&D lead of Spatial Audio, Lukasz Januszkiewicz. So both of them will be today with you, and I give the stage for you guys to start. As usual, you can ask the question in the chat, or we will answer them in the end. Moves in workplace and here in Zoom.
Right. Thank you, Bogdan, for introduction. Welcome, everybody. Let me start with the presentation. So here is our agenda for today. I will start telling about what is spatial audio in general, tell you about some definitions, what is spatial audio pipeline. Then I will present you shortly our spatial audio SDK concept and switch to the spatial audio rendering in a digital twins application. We'll talk about spatial hearing cues, object-based rendering, virtual scene description, and machine learning-based approaches for spatial audio rendering. And then Olga will talk in general about digital twins, what is it, how to use it, where to use it. And we'll conclude with spatial audio and digital twins, why sound matters, why spatial audio, what is the benefit of using it, something about use cases, and what are our plans. Okay, so let's start with the definition of spatial audio. So many of you probably heard different terms about 3D sound or spatial audio. They are used interchangeably. Some of people say that spatial audio is when the sound is attached to some objects or position and the user can determine the location or the direction of arrival of a sound. Another can tell that spatial audio is when the head, the sound responds to the head position. It is also known as a head tracking feature. Another will tell that sound is all around you, all around the listener, and matches the real physical or virtual space that he is currently in. And in general, we can tell that sounds just like the real world. So those are quite general definitions of sound. Once I heard a very nice definition that tells that spatial audio convinces you that the sounds are coming from the world around you and not from your headphones or speakers, and continuously adapts to the changes in the world and your movement through it. So what we can tell about all these definitions that they focus mostly only on the listening experience. But the spatial audio is something more. And I want to tell you about this. So we need to take a look at the spatial audio as a whole technology that has its pipeline, and we can distinguish here three development areas. The first one is I call it capture or production of spatial audio. So these are all the methods, techniques, algorithms, or devices, equipment that are used to produce the content that is going to be played as spatial audio. Another group of methods is spatial audio processing. So we can include here like spatial audio coding and rendering, some methods for scene analysis or decomposition, acoustic analysis of the scene, metadata processing, mixing and mastering, or interaction control with the user. So there's a variety of algorithms that are used to process the spatial audio. And the last stage or area is the presentation area. So this is the area that cares about how the spatial audio is delivered to the user. We can play the spatial audio throughout the loudspeakers, for instance, in cinemas, soundbars on a TV set in the house, and as a binaural reproduction through headphones, which is the most common use case. And today we'll focus on the binaural reproduction. So a few words about our spatial audio SDK concept. So our goal here is to take all these areas that I mentioned a slide before about spatial audio production, spatial audio processing and presentation, divided into some methods, algorithms, and implemented or compiled in the form of spatial audio SDK that can be further used in different application areas. So we have, for instance, areas related to spatial audio rendering in VR, AR, or game applications. We have some applications related to sound signal analysis, like detection, sound event detection, direction of arrival. And we have also some tools or applications that are related to capturing the sound field, generating the content, the spatial audio content. We will focus on the spatial audio rendering in digital twins application. So let me start with some details here. So sorry about that. So some technical details. So why do we here perceive sound from different directions? So there are some the so-called cues that our brain interprets, can interpret and distinguish the direction of arrival of sound source. So we have something like intraaural level difference, which tell us that the sound which is more on the right side will be heard more through the right ear than through the left. We have also intraaural time difference. The sound that is on the right side will arrive to our right ear faster than to the left ear. We have spectral cues, which tell us that some sounds that are lower, below, let's say, horizontal plane, will have some other spectral content, less higher frequencies, for instance, than the sounds that are above us. And we have other cues like airy reflections. So the sound that is emitted in the room, it is reflected from the walls, and these first reflections are called airy reflections. The other reflections are called late reverberation, and we have some other effects in general called propagation effects. The first group of these three cues are encoded in the so-called head-related transfer functions, which basically describe the channel that or the way that the sound has to go from the sound source, here it is our speaker, to our ear. So this function is, let's say, it's a mathematical representation of how this channel looks. The second group of these effects depends on the acoustic properties of the space that we are in. So if we have empty walls, the reflections will be hard because the sound is not absorbed by any soft materials. In a large hall like churches, the late reverberation will be very high because the area is very large and the sound is reflecting many times and so on. So this depends on the properties of the acoustic space that we are in. So let me explain you how the object-based rendering works. So we have our object here in a simple room with some walls and our listener. The green arrow is our direct path sound. So this is the direct path of the sound that comes to the ears, that arrives to the ears of our listener. We have some early reflections, as I mentioned before. first reflections from the walls. Here I marked only 2. Reverberation, which are late reflections, so we have more reflections from more than one wall. We have some other effects like diffraction, for instance, that is marked here with the purple color. So the sound is diffracted or occluded by some objects that are in the scene. And we have other acoustic properties such as absorption, transmission, reflection. Different colors of the wall indicate that they are from different materials, so they can absorb more the sound, for instance. Thus, the reflected sound will be weaker or stronger. So, this all features here can be encoded in the so-called room impulse response, which which is also a mathematical representation of how this sound propagates from this source to the listener. When we combine it with the head-related transfer function or head-related impulse responses that I described in the previous slide, we can talk about something like binaural room impulse response, which basically describes how the sound from the source from our sound emitter goes to the listener's left and right ear. So this is quite important term for today. Please remember this. So let me switch to the machine learning based spatial audio rendering that we are currently working on. So here we can see on the left side a virtual space, some, let's say two rooms with doors open, and on the right side we can see a top view map, which where the red dot represents our sound object that emits the sound, and the rest of the dots are the places where this sound is received. Each of the dots represents the energy with the level of sound energy that is received at a given point. So we can see that around the red dot, the color is the most light, the most yellow actually, which means that the received energy is the highest. When you go behind the wall, the sound is absorbed by the wall. Some of the sound is transmitted through the doors, but in general, it is already attenuated by this obstructors, and this level is low. The dark color means that the sound energy is very low. So our goal here is to estimate BRIR for each of this pair between the sound emitter and the receiver point. So there are many combinations of where the sound emitter can be and when the receiver can be. How we want to do this? So this is the high-level concept. We have our virtual space data, which describes for instance, the room that I showed you a slide ago. And we have user data, which is, for instance, the position and orientation of the user in this virtual space. And we have our machine learning based model that's taking into account this input data, estimates our binaural impulse responses. The binaural impulse responses, room impulse responses, can be further used in the spatial audio rendering process by application it to an arbitrary sound source, which is represented by a, for instance, wave file. So the question is how to train this model. I mean, the diagram is pretty simple. It looks very nice, but it is not easy to train this model in a good way. So this is the way we approach this problem. So we have, again, our virtual space data that describe an arbitrary space. We have simulation environments that creates a reference set of binaural room impulse responses. Why you can ask here why can't we use already the simulation environment in order to get these BRIRs? Because this process is very costly in terms of computation power, and it isn't possible to simulate such BRIRs in a real time. So we need to take care of this process offline. Then we have our representation of this virtual space with a set of binaural room impulse responses, and we perform our neural network training, which then creates our ML-based model. Then, as on the previous slide shown, ML-based model taking into account the user data and sound object data can estimate BRIRs. So this is a general concept of our approach to the machine learning based spatial audio rendering. I won't be going into any more technical details because I don't want you to get bored. So now I will let Ola to talk about the digital twins. Thank you.
Hi guys, Lucas, you will continue to share the screen?
Yes, of course.
Okay. So after a nice technical preparation, you will now understand what we mean when talking about spatial audio. But I will add you here more information about digital twins and how spatial audio works with and for digital twins. It will be much less technical, but I will show you how this all can benefit and can bring money working in business. So when you hear about digital twins, you probably will think about like similar twins or some twin robots, but these are not. Digital twin is a virtual copy representation of any physical object process system that you have in real world. So you have some equipment which is real, you can touch it, you can go around it, and you can make the same in virtual reality. This is called digital twins. It has all the characteristics, all the features, sometimes dimensions. You can make it exactly looking the same, functioning the same, behaving the same, accepting identical input data and providing relative output data. So you have something virtual and you have something in actual reality near you. Lucas, please, next. Mostly digital twins are used for simulation and testing. So before you start working with your actual objects, let's say it's some equipment, you can do any changes, any adjustments, settings, and try it on your digital twin before starting to break your real equipment. You can monitor how it behaves. You can add some elements, remove some elements, increase loading, decrease loading. And when you are satisfied with the behavior, with the look, with the design, you can start and try to do something with your real object without being afraid that you can break it, or you are aware of different behavior or some differentiations in behavior. So you are prepared and you know how to treat it. And of course, for training and education, before trying to drive some car, you can try to use it like a digital twin, or you can see how it behaves, and then it will be easier for you. Next slide, please. And the first case, like real example of how the digital twins are used here without the sound so far, is our actual customer, Valio. You can see a very nice white car with car lamps. Valio are the manufacturers of car lights, and their ultimate idea is to be able to design the car lights first inside the digital twin, and then to manufacture physical objects, because currently they need like 10-15 iterations of physical manufacturing of one car lamp with different modifications and changes before they get the car light that they want and which functions the way they want. So their idea is to run a couple of iterations in the digital twin to see how it is working, how it fits the car, how it looks, and then to make not 10, but one real physical car light, see how it is in real, then proceed and making iterations in the digital twin, and then make the second physical copy, the second physical model. So this will save money, this will save time, this is very sustainable, so they don't make tons of garbage of car lamps that are not used because they do not function the way they want. That's an example how the digital twin can improve manufacturing of physical elements, car lights. Can we move further? And digital twins as virtual copies, they can be used probably in any industry you can think of. First of all, they are very relative and useful where we have very complex and very expensive equipment, which requires a lot of training to work with which needs monitoring, so that not to spend tons of money and lots of time for it. You can work with virtual digital twins first. Or it can be even the healthcare, something drastically different, using test results, examinations results, whatever you do in hospital. We can create digital twin of human body, or not the human body, maybe some parts like heart or brain or whatever, which really makes it easier for the doctors to plan the treatment. Or, for example, pre-surgery preparations, they can work with digital twins first and then to proceed with real operations, which really increases chances for a good result or can help them during some procedures or operations. Of course, aerospace defense, the same expensive and very complex equipment, automotive, construction and real estate, which is very close to us because we have real use cases for them. Let's move further. And here is when I start talking how the digital twins and spatial audio work together. When we talk about virtual reality, first we think about what we see, so the visual part. But the sound we hear is very, very, very important as well. And currently, most of people developing or working with virtual reality, they try to make the picture the best they can. But making the sound the best they can will drastically improve the experience. Because when you see very nice, very vivid picture in front of you, especially if you are wearing headset and you don't see anything around you, and this doesn't have sound, it is not realistic. You will feel that something is wrong, because in real life, we have smell, we have taste, we can touch objects, we can listen to them. And in virtual reality, if we want to make your twin as realistic as possible, we also have to include as many aspects, as many senses as possible. And audio probably is the simplest way to make your experience there more realistic, more immersive. If you see someone opening the door behind you, and if it is really like behind, you will turn your head. And if you just see something opening or something falling without the sound, it will feel weird, at least for the way you perceive this reality. Next slide, please. And as I mentioned, the sound is important, but why spatial audio, spatial sound is important? Because it is way, way, way better. I heard it once and I like to repeat it many times. Once you experience the difference between like normal audio you are used to, like in most cases, and you compare it to spatial audio, you will never want to return back. You will want to use as many applications with spatial audio as possible and to make it as qualitative as it is possible, because it makes it really realistic. And as Lukasz mentioned, not like the sound you hear from the headphones right inside your ears, but it is like you are inside the virtual reality. Something is louder, as if it is closer to you, something further. You know that something is soft, not only from the visual perspective, but from the sound you hear from them. That's why if you want to make your digital twin, and if very realistic, and if it has the sound, it like makes some noises, spatial audio will be a game changer here. Next slide, please. Here, like the slide, how it improves, what benefit it brings from the business perspective. First, it attracts more users. Users want to have qualitative content. They want to use something nice. And if it is better, especially in terms of sound, and nobody else has the sound, they will go with the application or with the stuff you develop. And the second piece is accurate acoustic features. Sometimes the sound is very important, and the sound is the key features for some applications, for some digital twins, and for some cases we are working with. And with bad sound, not spatial sound, we won't get the result we want. And in the next actual use cases, I will show you how it works, how we can optimize our applications, and how it can save money using the spatial sound in a nice digital twin. Next slide, please. And the first is our use case for the client from construction industry. We made them, I would say we will proceed making them. Digital twins, both focused on visual and audio parts. They are a construction company from France. They're like one of the main tracks is manufacturing of window panels, but they also build buildings, and they are manufacturing different wall panels to decorate the interior of the apartment. So their idea was to be able to create digital twins of the buildings they are going to construct even before the actual construction is started. Why is it for? To be able, for example, to walk inside the building, to see the approximate dimensions of the room, and to listen what is the acoustics inside the room. Especially if they are working with different wall panels, they can make them soft and the sound will be more absorbed. If the window panels, glass panels will be bigger, the sound will behave itself in a different way. And in a virtual twin, they will be able to see different drawbacks, different things that can be changed, improved, some materials that have to be substituted, or walls making thicker or thinner, right before physically the object is ready and you have to make changes. So a lot of things may be implemented or planned or modified before it is physically constructed, and you have to break it and make it new for one more time. You can change everything in a virtual twin, saving cost and saving time, and start building like right more or less the option, the configuration you want. So that was the construction case, and please the next slide. Pretty similar, but a bit different. It is automotive case, and here we also like offer digital twin that goes with spatial audio and for purpose for automotive, for the companies that are manufacturing cars. And here we have two ideas how spatial sound can improve digital twins of the cars. First is more for demonstration purposes, for buyers, for people to be used in the car shops, which is like already partially implemented. When you want to buy a car, you go to some shop, to some dealer, but there are not all the car models with all car configurations that are available, for example, in their brand. There are some 2 or 3 of them, but you can put on VR glasses, VR headset, and you can see, you can test drive any car with any configuration you want. And adding special audio, which is pre-recorded for each model, for each specific configuration, and that can be tens, hundreds of them. The users will be able to get more realistic experience because they will hear, for example, how the music sounds inside the car, how the noises from the street are perceived inside the car, or maybe you open the window or close the window, so that it will make the experience of that car, which is not available inside the shop, very, very realistic. And the implementation of this solution is much easier because in this case, we just we record the sound of actual car models and then just connect and implement them into the virtual car so that you hear and see. The second solution is more complicated but it brings more value. It is the simulation, and it should be used not by the buyers or car drivers. It is used on the stage of car design and manufacturing. When some new model is designed, the digital twin is created considering the acoustic properties of the car, of the materials used inside, outside, the thickness of the materials, and the designers can test how, for example, these or that tires will sound. Or maybe if talking on the speakers inside the car, people from outside will will hear you. So some changes should be done. Or maybe something should be made thicker, or maybe some decoration materials should be substituted. So it is to make something better before implemented it in real world, also saving time, saving money, and giving actual feedback without having the real car model, for example, in your factory. We also have a couple of potential clients, like already in SoftServe, who are primarily interested in this track. So we are continue working with it. So let's see how it goes. Because they are interested, we are interested, I think something will work out of it. Next slide, please. Oh, it is almost the final one. This relates to spatial audio for digital twins and our plans for R&D. Spatial audio technology is very hot, I would say, on the market now, because it turned out to be well accepted by the users. So everybody want to have it. Everybody want to have spatial audio, nice and qualitative. So it will be developing and developing in the next years. And we want to be like on the same page. So we would like to proceed our work with spatial audio in two directions. First, Lukas partially mentioned it. We are developing our spatial audio SDK. Currently, we are implementing it in the form of POC to demonstrate that we know how to work with spatial sound, how to implement it to the existing applications, or maybe to the applications that only have to be developed already with the spatial sound, and get the feedback from the customer or potential customer to know in which direction to proceed. So this SDK may be treated as a service or as a separate product, which also has potential for development. So if treated like a product, we are planning to have some Unity, which is already made, or Unreal plugin that can be added and like purchased as separate plugin, separate application. And the second track is research. As we are R&D, we need to know more about the technology, more about its limitations and capabilities in omniverse, in metaverse, how to make it sound. So this will end in some research papers that will be further shown, and we will decide how to proceed in what direction. So currently we are working on spatial audio, and we are planning to continue working with it for the nearest future series. And I suppose that was the last slide.
Yeah, so maybe let me add a few words about the SDK and the research here. So with the SDK, we are currently working on the proof of concept in the form of Unity plugin that can be integrated in any Unity-based application in order to demonstrate the spatial audio rendering features based on our technology. And regarding the research, yes, we have now finished one paper that will be published in 4 weeks, actually, in International Symposium on Sound Processing and Tone Mastering in Warsaw. And the goal of this initiative is to discuss with the academic society and with other experts, also to get some more technical feedback about the technology. Yeah, that would be this. Thank you.
So if I understand you correctly, it was the last, I would say, node related to SDK. So guys, thank you for the great presentation around the topic of spatial audio for digital twins. Audience, if you have any questions related to the topic, you can ask it in the chat, both here in Zoom or on Workplace. We were quite concise today, so it's like great space for the questions, so I encourage you to do that. Still, we have like one question for our champion, Marta, related to today's session. Do you need special headphones to experience spatial audio? Can it be done without the headphones like speakers? And probably what is the difference, right?
Okay, I like the question. So I can have two answers: a very quick one and more sophisticated one. So the quick one is no, you don't need any special headphones to experience spatial audio, unless they have only like one headphone for one ear. To experience spatial audio, you need to hear it through 2 ears. And so as long as the headphones have 2 transducers for left and right ear, they should be good enough for experiencing spatial audio. On the other hand, and here comes the second answer, is it is known that in order to perceive spatial audio or the location of sound sources in a correct way, also a crucial role plays the spectral cues that I mentioned on one of the slides. So if the headphones have a poor quality frequency response, for instance, they lack of high frequencies, then the experience cannot be as good as it could be. So some of the tools used for spatial audio rendering, for instance, binauralization, they have even built some presets for headphones that are available on the market in order to adjust this frequency response, so the final experience is even better. I hope this.
And yes. Yeah, I hope you completely answered the question. It's rather interesting whether SDK will cover both of the type, like headphones and just sound from the speaker, or it's only focused on binary like this case.
So we started from the binaural reproduction because it is like the most commonly used by the users. Any type of virtual reality application or gaming application, most of the users uses headphones. But no, we are not going to limit only to binaural reproduction. We are also planning to implement algorithm for the speaker layout, spatial audio rendering.
And that's interesting. Like for digital twins, like what kind currently of like audio sound reproduction is used? Are all of them a spatial audio, or maybe some kind of? Is it any other types of standards that currently is used for digital twins overall, like for sound reproduction in virtual reality? I mean, just the plain one, I don't know, some another type of libraries and techniques that might be used instead of digital twins. So your other is just like standard one, a special one, and that's all.
Sorry, I didn't get the answer. The question.
This interesting question. There is like only standard audio without like all of the features that contain spatial audio, or there is something in between, like I don't know, like I mean, like standard audio just when you don't have, for example, I believe that one of the main features is when you can interact with the object, like yeah, and for example, if it falls down, you hear, you know, like you can like hear the sound in reproduct. For example, you fall down, I don't know, the glass, and you hear how it was broken. And it's interesting whether there is some, I don't know, different types of, in terms of spatial audio, which cover some specific functions, like just, I don't know, the like type of that do not cover interaction with the object, and the other one cover like interaction with the object as well, and how does it influence on the type of spatial audio.
Yes.
From that perspective.
So yes, it can be, let's say, partitioned into different levels. Probably you all know that the very basic spatial audio is a stereo sound that we have on the CDs. You can already there distinguish some kind of directional variable of different instruments that are distributed on the scene. Many people think that the spatial audio starts when you can hear the sound from behind or from upper or lower directions. So these are like this additional features. And the other level is the interaction. So you can manipulate the sound sources. You can move them around or mute some of them, change the level of the sound they emit. So yeah, all depends on the application and on the system that you are currently using, actually.
That's interesting. That's interesting. A lot more to dive deeper. We'll see one more question. The project for construction client. What has been currently done, and what are the plans? The next step in terms of audio. Probably question, yeah, to both of you.
Okay, so currently we were working on the binaural reproduction of the sound samples that were provided by the client. So it's like the very first stage. In the second stage, we will be working on the let's say more universal approach. So there won't be a need to. Okay, let me refer maybe to the spatial audio pipeline. There are different ways of production of content. One of this is capturing. So here was the case where the client captured some sound in a specified format, and our goal was to develop methods that will play this sound in a spatial way on headphones. And in the second stage, we want to develop this further, so he won't be forced to capture this spatial audio, but it will be, let's say, already processed and then rendered to the headphones.
And I would like to add that in terms of visual part, because currently this is like a bit separate tracks. It was also like a POC. We have in Omniverse a glass cube with different types of glasses, with different thickness, with different coating. And first, what we try to do is to make it as realistic as possible in terms of light, transition, reflection, some absorption. So how the ideal option, the ideal final result will be to have the glass in Omniverse behave as in real world. When the sun shines, how the rays go through it. So this is a glass cube with some types of glasses, and they have some physical characteristics identical to the ones in real world. but it will be like more and more features both from audio and from the video parts. When later it will be something like more or less looking like a house with windows and different panels inside. It seems that from audio part, it was something like a classroom. And from visual, it was a very simple but nice looking like glass cube.
Okay, thank you for the answers. As I can see no questions in the chat anymore, so I think we can come to the finish of our session. So Lucas, Ora, thank you for the great presentation around spatial audio of digital twins. I believe it was insightful for most of today's participants. And if you have any more questions related to how the research is going, or whether there are any other use cases or the use cases you just observed related to the companies you're interacting with, you can always reach Ola and Lucas so they can provide you with more information. Thank you, everyone. Have a good day. And
Thank you.
see you in a month. Bye-bye.
Thank you.
Bye.